Let's take a look at an example where now we're going to use this idea of the limit process to find the exact area underneath the curve in some region. So for this, we're going to use the limit process to find the area bounded by y equals 3x minus 2 and the x-axis on the interval 2 to 5. So if we think about what this is going to look like is we have some line that does this, and we're looking on the interval 2 to 5. We would like to calculate this area in here. So when we're looking at using rectangles, again, we're saying that the goal is that we're going to have some type of rectangles in here, but we're going to try to take the limit as n goes to infinity. So we're going to take an infinite number of rectangles. Notice also when we have an infinite number of rectangles, what happens to the width of each of these rectangles? So as the number of rectangles goes to infinity, the width is going to 0. These become infinitesimally small width rectangles. So it's weird to think about, but indeed, we have these rectangles where really the width of them is going to 0, but it still works. All right, so let's pinpoint some of the information from this example that we need. So our function f of x is 3x minus 2. For the sake of understanding the formulas that we have a's and b's present. So a is going to be 2, b is going to be equal to 5. Now, this function, again, this is continuous, and it's also positive on this, so that is great. Now, what we also need to do is we have to figure out for n rectangles, then what is this width that we have? So our delta x, we said this is b minus a divided by n. This is going to be 5 minus 2 divided by n, which is 3 over n. So when we have n rectangles, each of the width is going to be 3 divided by n. And the last thing that we need in our formula is going to be these c sub i's. So we can use right endpoints. Our right endpoint said that c sub I was going to be a plus I delta x. So we have our a, which is 2. Our I is going to always be there. That's going to help us know which rectangle we're working with. And then we have times 3 divided by n. That is our delta x. So now that we have this, we can move on. As a note, you can choose left or right endpoints. Theoretically, nothing is going to change with this because once our rectangles become infinitesimally small and there's an infinite number of them, the left and the right endpoint are basically the same value. So you choose the easier one, which I think the easier one is always the right endpoint. So if we look at our area formula now, our area is going to be the limit as n tends to infinity, the sum from I equals 1 to n of f of c sub I times delta x. So this is the formula that we have for finding the exact area using a limit. So I take the limit as n tends to infinity, the sum I equals 1 to n. I now plug in the things that I know. So my f is going to be 3x minus 2, but at this value. So I'm going to take 3, I'm plugging in this, 2 plus 3i divided by n minus 2. So remember, this here, this was going to be 3x minus 2, but instead, I guess, 3 times c sub I minus 2, but our c sub i's are those. And I multiply all of this by my delta x, which is 3 divided by n. So I have this expression. You're always going to have i's and n's present in here, and we just have to work with them as variables. So I just start to simplify things. So I have the limit as n tends to infinity. I have the sum from I equals 1 to n. I distribute the 3 inside, so I have 6, but I'm going to be subtracting a 2, so that gives me 4. And I distribute the 3 inside to the second term, and I'm going to get a 9i divided by n, and this is times 3 over n. Now remember, I said we have to work with the sum first, then take the limit. So when I'm just dealing with the sum, this I is really the variable and n is truly a constant. So I'm going to start to use the rules that we had for sums to start to pull things out of the sum, but not outside of the limit, only outside the sum. So I have the limit as n tends to infinity. I have 3 over n. I have the sum from I equals 1 to n, 4 plus 9i divided by n. So I pull out the 3 over n. Now I can separate these two into two different sums. So I have this is equal to the limit as n tends to infinity of 3 over n. The sum from I equals 1 to n of 4 plus the sum from I equals 1 to n of 9i divided by n. So there will be lots of parentheses in here. That's good. Now this one I can calculate the sum of. This one I'm going to pull out the constant of 9 over n. Pull that out. So I have the limit as n tends to infinity of 3 over n times the sum from I equals 1 to n of 4 plus 9 over n, sum from I equals 1 to n of I. So using the formulas that we had for each of these, this is equal to the limit as n tends to infinity of 3 divided by n. This becomes 4n. And then this one becomes 9 over n times n plus 1 divided by 2. Oh, one more parenthesis. And now we can start to simplify some things. So I can cancel out this n with this n. So what I have here is I have the limit as n tends to infinity of 3 over n. I have 4n plus 9 halves times n plus 1. Then I can distribute this 3 over n inside there. So I have the limit as n tends to infinity of 12n over n plus 9 times n plus 1 divided by 2n. Then what I have here is I have these two expressions that if you'd like, you could combine, you could have find common denominators, do whatever you'd like. We could deal with each of them separately, but I'll deal with common denominators. I have 24n plus 9n plus 9. So if I distribute the 9, find common denominators, and combine all of this, I have this over 2n. So this is the same as the limit as n tends to infinity of 33n plus 9 divided by 2n. Now we take this limit as n goes to infinity, we get infinity over infinity. That is an indeterminate form. What can we do? Well, you could divide by the highest power of n from the denominator. Do that. Or we use L'Hopital's rule. So let's use L'Hopital's rule because we know that. Take the derivative of the top and the bottom. So I have the limit as n tends to infinity of 33 over 2, which is our final answer of 33 over 2. So this is the area of that shape that we found. Exact area is 33 over 2. For that case, because the shape that we had was a trapezoid, you could use the equation of a trapezoid, calculate the area, and see that the area is indeed 33 over 2 to verify that. But we see that for a nice example, and so this process of working through the algebra, right now at the board, it looks very intimidating, but hopefully step by step, you just work through the necessary things of using your regular distribution, everything like that, but make sure that you understand all of the rules of summation and how you can manipulate those, and then knowing these specific formulas for the sums of i's with the sums of constants or I squareds and so on and so forth. So there we go. That is an example from start to finish.